Okay. Hello everyone. Welcome to AAT concept video. My name is Narala Siddhartha. My roll number is 20951 A6744. My branch is computer science engineering with data science as specialization. So today my subject is theory of computation. So I'm going to discuss about the deterministic finite automata in this subject. So let's start. So I mainly divided the content into three parts. The first part, I'm going to discuss what the finite automata is, and I'm going to give a detailed preview about the finite automata that are used in the theory of computations. So in the second part, I'm going to discuss about the types of automatas, different types of finite automatas that are present. So in the third part, I'm going to discuss about the deterministic finite automata and its working. So let's start. So finite automata. So finite automata or finite state machine is the simplest machine that is used for recognition patterns. It is an abstract machine that has 5 elements or tuples. So basically finite automata is described using a 5 tuple system. We will discuss about the elements present in the tuples and each element among the 5. So it possesses a set of states and rules that are used for moving from one state to another, but it is dependent on the applied input symbol. Essentially, it is pretty much an abstract model of a digital computer. So it is a mathematical model of computation. This abstract machine can be in exactly one of a finite number of states at any given time. The finite state machine FSM can be in exactly one of a finite number of states at any specific time. So a finite state machine can transition or change from one state to another in response to some inputs. A finite automation is defined by a list of its states, its initial state, and the inputs that trigger each transition. You can observe the behavior of state machines in various devices in modern society that perform a predetermined sequence of actions depending on the sequence of events with which they are presented. The finite state machine possesses less computational power than certain other models of computation like the Turing machine. So the computational power distinction signifies that there are computational tasks that a Turing machine could perform but finite automata can't. So finite automata are used to recognize patterns. It takes the string of symbol as input and changes its state accordingly. When the desired symbol is found, then the transition occurs. At the time of transition, the automata can either move to the next state or stay in the same state. Finite automata have two states, accept state or reject state. When the input string is processed successfully and the automata reached its final state, then it will accept. Finite or otherwise it will reject when the string has been terminated its input in middle of the finite automata. So if we are giving input from the symbol, so when the symbol is completely iterated and even after the complete iteration of the symbol doesn't fetch you to reach to a final state in the finite automata, then it is going to reject, and this is known as the rejection in finite automata. So finite automata can be represented by input tape and finite control. Input tape, it is a linear tape having some number of cells. Each input symbol is placed in each cell. So finite control. The finite control decides the next state on receiving particular input from input tape. The tape reader reads the cells one by one from left to right, and at a time only one input symbol is read. A finite automation is a collection of 5 tuple. So here before we have discussed about 5 tuple. So here is the 5 tuple and the elements present in it are shown. So here q, epsilon, delta, Q naught F is given. So here Q is nothing but the number of states that are present in finite automata, which are basically represented as Q1, Q2, Q3, so on up to n, where n represents the number of states present in the finite automata. So summation is sigma is nothing but the set of all the input symbols that are present in the finite automata, which accept these only these symbols. So Q naught is nothing but the initial state. It is also called as a start state. It is basically represented within a circle followed by an arrow mark before it. So F is nothing but a final state. Okay, this final state is the state which tells the finite automata that it has accepted the string which has given to the finite automata. So here delta is nothing but the transition function. So when a string is given to finite automata, so how the finite automata is computing and traveling from one state to another state is explained in this transition function step by step. So all these steps together is known as a transition function, which is represented by a delta. So here is a small picture which represents the finite automata actually. So here the work, home, bed, which are inside the circular shape are nothing but the states we call in finite automata, and the arrow marks are the directions of the state which reaches to the another state on giving a particular input. So here the take, train, wake, sleep are nothing but the inputs which we call as strings in finite automata. So this is the example of the finite automata. So what are the applications of finite automata? So finite automata has several applications. Some of them are very important in designing lexical scanners. They are also critical in designing spell checkers. They are vital in sequential circuit design. They are particularly useful in designing text editors actually. In addition to these applications, finite state machines are also used in linguistics, computer science, electrical engineering, etc. And in the domain of computer science are utilized for modeling of application behavior. So apart from all these applications, I want to explain one of the most important application is it is used in natural language processing. So which is a growing sector in these days. So let's talk about the type of automatas present. Okay, type of automatas. There are mainly two types of automatas. They are DFA and NFA. DFA stands for deterministic finite automata. NFA stands for non-deterministic finite automata. So what is DFA? DFA refers to deterministic finite automata. As we have discussed before, deterministic finite automata refers to the uniqueness of the computation. In the DFA, the machine goes to one state only for a particular input character. DFA does not accept the null move. Okay, NFA stands for not deterministic finite automata. It is used to transmit any number of states for a particular input. It can accept the null move also. So some important points about DFA and NFA are here. Okay, here every DFA is NFA, but every NFA is not a DFA. So we'll discuss about this sentence in the next slides. Okay, there can be unique final states, multiple final states in both NFA and DFA. DFA is used in lexical analysis in compiler. NFA is more of theoretical concept. So let's discuss about deterministic finite automata. So what the deterministic finite automata is? It is shortly known as DFA. Deterministic finite automata refers to the uniqueness of the computation. The finite automata are called deterministic finite automata if the machine is read an input string one symbol at a time. In DFA, there is only one path for specific input from the current state to the next state. DFA does not accept the null move. That is, DFA cannot change state without any input character actually. So DFA can contain multiple final states. It is used in lexical analysis as we have discussed before. So this is an example of a DFA. So what's the main difference between the DFA and NFA is, in DFA only one input is given. It means a state can contain multiple inputs, but each of those multiple inputs may contain only a unique input value. But same different paths with the same input cannot exist in DFA unless NFA. NFA can have such privilege, and DFA, deterministic finite automata, cannot also accept the null values, but whereas DFA can accept. In deterministic finite automata, if a null value is given, then it does nothing. It stays in the state in which it has already been. So here Q0, Q1, Q2 are the states. Q1 is the final state. So a path is given from Q0 to Q1 through A as input, and similarly Q0 to Q2 through B. This is a simple one. There may be complex deterministic finite automatas also based on the logic that we want to prepare on. So here, as usual, it is also determined with the help of phi tuple, so which is given as Q epsilon Q naught F delta, which I have discussed before. So it is graphical representation we have discussed before, what are represented like that. Okay. So this is an example. Okay, basically. Thank you.